In this lecture, we will extend the idea of Bezier curves to include more than just 3 points. In the diagram, the point P sub A, B, C traces out the Bezier curve for A, B, and C. The coordinates of P sub A, B, C are given by this vector equation, where t is from 0 to 1. The real number t represents the ratio between segments on the diagram. T is equal to the distance between A, P sub AB, divided by the distance between AB and capital B. It is also equal to the distance between B and P sub BC, divided by the distance between B and C. And for the last ratio, T is also equal to the distance between P sub AB and P sub ABC, divided by the distance between P sub AB and P sub BC. To see what the curve that P sub ABC traces looks like, let us start t at 0. The direction that the curve will take will be from point A towards B and then towards C. At t equals 0, P sub ABC starts at the point A. Sliding t towards 1 would generate a curve that starts towards B, but does not pass through B, and then curves towards C. We extend this idea to include a fourth point D. The new Bezier curve will still start out at A, move towards B, and then towards C, and then towards D. Like we did with P sub ABC, we will generate a Bezier curve, this time using the 3 points B, C, and D. This Bezier curve will start out at B, move towards C, and then towards D. We take a point P sub CD between C and D, so that the distance between C and P sub CD divided by the distance between C and D is equal to t. Then connect P sub CD to P sub BC. On this segment, we obtain the point P sub BCD that traces the Bezier curve from B to C to D. And the distance between P sub BC and P sub BCD divided by the distance between P sub BC and P sub CD is also equal to t. Now, instead of writing out the formula for P sub BCD, we seek out the point that will trace the Bezier curve for A, B, C, and D. We'll call this point P sub A, B, C, D, which is on the segment between P sub ABC and P sub BCD. As with the other ratios, we require the ratio between the lengths of these two segments to be equal to t. Let us take a look at the shape of the curve that P sub ABCD traces. At t equals 0, P sub ABCD starts at A. And as t increases, P sub ABCD slides towards B, gets pulled towards C, and then swings towards D. So that P sub ABCD and D coincide at t equals 1. What we have to do now is to find the parameterization for P sub ABCD. Let us bring back all the ratios between pairs of segments formed by the different Bezier points. Each of the ratios is equal to t. Because of this, we can use the parameterization for P sub ABC as a basis. Starting off with P sub BCD, simply changing the vectors or points that we use in the formula for P sub ABC, we get this formulation for P sub BCD. With P sub ABC and P sub BCD as endpoints for P sub ABCD, and using the parameterization of a line segment, we easily get a parameterization for P sub ABCD. We replace P sub ABC by its parameterization to get the first few terms for the parametrization for P sub A, B, C, D. Replace P sub B, C, D by its parametrization and we get the rest of the parametrization for P sub A, B, C, D. Combining the terms according to the different vectors, this is the form that we get for P sub A, B, C, D. Let us turn our attention to these factors, which are the coefficients of the vectors or the points that are used for the parametrization. Let us ignore the vectors and take only the coefficients that involve t. We end up with a sum that looks like this. If we set A to be equal to the quantity 1 minus t and B equals t, then running down the list of terms, we have A cubed for this term, 3A squared B for the next, 3AB squared for the next, and finally we have B cubed. So what we have is really just the expansion of the cube of the quantity A plus B. Now, this entire thing is actually equal to 1, but that is beside the point. What this seems to lead up to is that if we are going to generalize this idea to take a look at Bezier curves for P sub 0 through P sub n, then we should take a look at the expansion of the nth power of the quantity A plus B, where A is equal to 1 minus t and B is equal to t. And on this note, we write down the parametrization for the Bezier curve for P sub 0 through P sub n. And we can write this out in the following summation form. This fraction, n factorial, over the product of I factorial and the factorial of n minus I, is what we call the combination number. It is sometimes read as n choose I. We can write out the parameterization in this alternate summation form. And here, t goes from 0 to 1.